Welcome to electromagnetic radiation. So electromagnetic radiation is a form of energy that's emitted and absorbed by charged particles, and this exhibits wave-like behavior as it travels through space. So electromagnetic radiation is sunlight, microwaves used to heat food, microwaves used to carry cell phone signals, maybe, X-rays, heat radiating from a fireplace, radio waves that carry television, cell phone signals, Wi-Fi signals. These are all different forms of electromagnetic radiation. So light is different from visible light. Light means any electromagnetic radiation. So all electromagnetic radiation is light. Now visible light refers to just a very narrow portion, just a very specific portion of the spectrum that's only the portion that humans can see. So light is a wave, but it's also kind of a particle too. But waves have frequency and wavelength. So frequency is denoted by nu, N-U. So that's this symbol here. It looks sort of like a V. So frequency is the number of waves that pass a given point of space in a given time. So we measure this in terms of hertz, where 1 hertz is 1 reciprocal seconds, so 1 over seconds. And wavelength, which we symbolize lambda, that's the distance between some point on one wave and the same point on the next wave. And we measure that in meters. So here I've got a little diagram, and up here on the top we have wavelength in meters. So we have very long wavelengths over here. This is 10 to the 3, 10 to the 2, 10 to the 1, 1, 10 to the minus 1, and so on, down to 10 to the minus 12. So on the left side we have long wavelengths, and on the right side we have short wavelengths. Now, I also have 2 more scales down here. We have frequency, which is this scale, and these are low frequencies, so here is 10 to the 6, 10 to the 7, and so on, up to 10 to the 20. So again, this is frequency, so this is waves per second. So down here, at 10 to the 6, that's 10 to the 6, so 1,000,000 waves per second pass by some point in space. So that's like radio waves. As we get higher in frequency, you notice we also get higher in energy. So the bottom scale here is energy of 1 photon. Now this happens to be measured in electron volts, but the general idea here is that as we increase the frequency, as we go from low frequencies to high frequencies, we're also increasing the energy. And so here we have the high frequency, high energy end of the spectrum, and here we have the low frequency, low energy end of the spectrum. Now let's go back to our wavelength. We said that the long wavelengths were on this side, but long wavelengths are low frequencies, low energy. High energy, high frequency were short wavelengths. So the closer together you pack those waves, the more energy they're carrying, which seems to make sense. If we have waves on a pond, let's say, if we get 1 wave every second, we're just getting a little bit of energy. Now if we have the same height wave, but now we have 2 waves per second, well, we're getting twice as much energy. And if we have 3 waves and 4 waves, we're getting more and more energy. So the more waves we have, the more energy we have. So the higher the frequency gets, the higher the energy is. But the waves are propagating, they're moving at exactly the same speed, no matter what the frequency is. Which means that if we have more waves in a given time, each wave must be shorter. So as we move from this side of the diagram to this side of the diagram, we have to be increasing the frequency. We're increasing the number of waves that go past every second, but the speed of the waves moving is the same, which means each wave has to be getting shorter. So the high energy side is short wavelengths. The low energy side is long wavelengths. So, long wavelengths, the low energy side, are things like radio waves. Right? So AM, FM, radio, cell phones. Next we get to microwaves, and then we get into the radar spectrum. Then we get into the infrared. And then just a very small portion here. So just from this side to that side, that's the visible spectrum. So there we go from red on the low energy side, red, orange, yellow, green, blue, indigo, violet. The violet is the high energy side, and then we get to the ultraviolet. And now remember, the ultraviolet, the UV rays, those are the rays that when they hit your skin, they can cause skin cancer. And so those are higher in energy than the light that our eyes are able to detect. Now our eyes can't see any light down here. Our eyes can't detect radio waves or microwaves or infrared. Now, there are some animals that can detect infrared, like some snakes can see the infrared, at least some portion of the infrared. So this is how we say that snakes can see heat, because they're seeing in the infrared region of the spectrum. So as we get to higher and higher energies, we get to ultraviolet, then we get to the sort of the soft X-rays, which don't penetrate too far into human tissue. Then we get hard X-rays that penetrate very far, very deeply into human tissues, and then gamma rays, which are really, really high in energy. Right? So note that our sun puts out radio waves, microwaves, infrared, visible light, ultraviolet, and some of the X-rays. Right? Our sun isn't putting out too much of the gamma rays, but it's putting out energy in the whole spectrum. But we don't see all of that. Now, part of why we don't see it is because a lot of this stuff gets absorbed by the atmosphere. The radio waves get absorbed by the atmosphere really, really well. And the reason for that is also the same reason why we use microwaves to heat up our food. So, in this region, there's a range where water molecules absorb the energy. Now, there's lots of water molecules in the air, and there are lots of water molecules in most of our foods. And so, if we put out energy that's at that exact, or if we put out light, electromagnetic radiation, that's at that specific frequency that water will absorb at, we'll heat up those water molecules. And as we heat up those water molecules, we're heating up our food. Because a lot of our food has a very high water content. But this also explains why your microwave does very well in heating certain things that have lots of water in them, like a soup. It does very well heating up soup. But it does very poorly in heating up something like bread, which doesn't have as much water in it. It also tends to dry out the bread because the water that is there gets heated up, turns into steam, and leaves the bread. And so now you're left with a very dry hunk of semi-hot bread dough. So, of the electromagnetic spectrum, again, we're only seeing in the visible part because any higher in energy than that, and the atmosphere does a pretty good job of filtering out, of absorbing that radiation. The atmosphere does a good job of absorbing in the ultraviolet, and it does a pretty good job of absorbing a lot of stuff in the infrared. Not all of it, but a lot of it. And so we see in the visible, probably, largely because there's a lot of visible light around, and if we got any higher energy than that, there wouldn't be that much left at Earth's surface. So here's another diagram showing the electromagnetic spectrum. It shows that radio waves penetrate the Earth's atmosphere really well. This is why we use radio to communicate. We use cell phones and AM, FM radio, things like that. Satellite signals operate in this region. The microwave doesn't penetrate Earth's atmosphere very well because, again, there's lots of water around. The visible and some of the infrared penetrates, but then the ultraviolet X-ray doesn't penetrate all that well. But I also want to show the scale of these waves. So for something like a radio wave, that's 10 to the 3 meters long. Now 10 to the 3, that's 1,000 meters. That's like a kilometer. That's roughly the size of a building, a tall building. Right? And now, we don't have buildings a kilometer tall, but Maybe we'll get there. But sure, certainly, the length of a building, the height of a building, that's about the same length as a radio wave. Now as we get to microwaves, that's shorter than we are. That's about a centimeter long. That's not that long. But that also explains why, if the microwaves are that long, why the screen on your microwave can have those holes in it. It doesn't need to be longer than the microwaves are. If the microwaves are only roughly a centimeter long, those holes can be up to a centimeter or so. So then we get to something like infrared, which is 10 to the minus 5 meters. That's pretty darn small. That's smaller than the point on a needle. And then if we go even smaller to the visible, we're getting about the same size as a bacteria, a protozoa. And this explains why, if we go any smaller than that, to molecules, visible light doesn't see it. We can't see molecules with visible light because the molecules are smaller than the wavelength of light is. So if you imagine the wavelength of light as being like a net, well, we can't trap something that's smaller than the holes in the net. We can't see atoms using visible light. It's just not possible. So we have to use something that has a shorter wavelength. Maybe we could use ultraviolet or X-ray light, but X-ray light has its own problems. Those can do bad things to our skin and tissue. So we get to X-rays. They could potentially, that's about the same size as an atom. And then gamma rays at 10 to the minus 12 meters or so, that's the size of an atomic nucleus. It's really, really tiny. Now, down here, you can see this says temperature of objects at which this radiation is the most intense wavelength emitted. So, at very, very cold temperatures, like 1 Kelvin. At 1 Kelvin, the most intense light that's given off is here in the microwave region. If we heat up to 100 Kelvin, this is still pretty cold because that's minus 173 degrees C. Well, now we're giving off in the upper infrared, we're just maybe starting to give off in the visible, just a little bit. As we move up higher to 10,000 Kelvin, now that's pretty darn hot. Now we're giving off in the visible, starting to give off in the ultraviolet. We move up higher to 10 million Kelvin, now that's where we're giving off in the upper X-ray region. So, when you see something that's red light, that's cooler than something that's giving off yellow light. Unless it's something like a television, right? But if it's glowing because it's hot, if it's glowing red, it's cooler than if it's glowing yellow. And if it's glowing white, it's really, really hot. Because that means that it's farther to the right here, right? It's giving off a good bit of ultraviolet radiation at that point. So this is one reason why we talk about things in terms of television displays or computer monitors or light bulbs in terms of the color temperature. The color temperature, the cooler that temperature is, the lower that temperature is in Kelvin, the more red that light is going to look. The more red or the more yellow. The higher the temperature is, the more blue or the more white that light is going to look. Okay. So one other thing about light is that it all travels at exactly the same speed in a vacuum. So the speed of light in a vacuum is symbolized c, and that's 2.998 times 10 to the 8th meters per second. Now, we also know that the speed of light is equal to the frequency, nu, times lambda, the wavelength. Right? C equals lambda nu. So that's the wavelength times the frequency. That is equal to a constant value. Which means that as the frequency gets higher, the wavelength has to go down in order to keep the product of those two constant. That's what we saw in those two diagrams, right? As we move to higher frequencies, we got higher in energy, but lower in wavelength, shorter wavelengths. So, if we want, we can now calculate either the wavelength or the frequency given the other one. So if we want to calculate the wavelength of light that has a frequency of 7.26 times 10 to the 14 hertz, well, we know c equals lambda nu. We can solve that for lambda, our wavelength. So lambda equals c over nu. Well, we know c, the speed of light, is 2.998 times 10 to the 8th meters per second. We divide by our frequency, 7.26 times 10 to the 14th hertz. And here I've changed hertz into 1 over seconds. So our 1 over seconds cancel, we're left with meters. And we have 4.13 times 10 to the minus 7 meters. And that was electromagnetic radiation.